the relationship which relates the refractive index of the glass to the speed of light in air is given by this: n equals to c over v, where n is the refractive index and v is the velocity of light in the medium. So let's see what information can we get from the data of ray 1. So to calculate the velocity of the light in the medium, we know that we have a fiber which has a 1 kilometer length, which is equivalent to 1000 meter, and the time taken for the light to complete the whole trip is 5 microseconds. So the velocity of light is simply given by 1000 meter divided by 5 microseconds, and this is equals to 2 times 10 to a power 8 meter per second. And c, which is the speed of light in air, is also given as 3 times 10 to a power 8 meter per second. So n will be equals to 3 times 10 to a power 8 divided by 2 times 10 to a power 8, and this is equals to t3 divided by 2, and equals to 1.5. Alright, let's look at part B. So we need to calculate the angle of reflection x for ray 3. So according to Snell's law, n is given by sine of incoming ray divided by sine of the refracted ray. So, and in this case here is given by sine 35 degree divided by sine x. And then from part A, we know that n is equals to 1.5. So by having this relationship, we can exchange their position, rearranging their position, and this is what we get. Sine x would be equals to sine 35 degree divided by 1.5, and x would be equals to inverse of sine for the entire expression, sine 35 degree divided by 1.5, and this gives 22.48 degree. And since all the figures are given in two significant figure, so this will be equals to 22 degree. And there's another method to solve these questions, which is to make use of the information that we get from the property of ray 2. So, and again is given by the relationship of Snell's law. So n is equals to sine 35 degree divided by sine x, and equals to sine 20 degree divided by sine 13 degree. And this is the information that we can get from ray 2. So rearranging the equation, we get sine x equals to sine 13 degree multiplied by sine 35 degree and divided by sine 20 degree. So by taking the inverse of the sine theta, we arrive at x equals to 22.2 degree, and by only taking two significant figures, then we arrive at 22 degree, which is exactly the number that we get by using the first method. Alright, let's look at part C. At time t equals to 0, a single pulse of light enters the optical fiber of length 2 km. The pulse lasts 0.1 microseconds, and figure 9.4 in the paper shows the brightness of the pulse of light that leaves the fiber. So by using the figure 9.3, we need to explain what we see in figure 9.4. So let me quickly draw out what we see in figure 9.4. So it takes about 10 microseconds to see the first pulse, and then at 10.3 seconds we see the second pulse, and then at 10.8 microseconds we see the third pulse. Alright, so the reason why we see three different pulses by having a single pulse of light entering the optical fiber is simply because this is a multi-mode fibers, and it follows three different paths. Namely the path for ray 1, ray 2, and ray 3. And the reason for me to say that is that by looking at figure 9.3, if we look at the last column of the table, it says that the time spent in 2 km cable for ray 1, ray 2, and ray 3 is 10 microseconds, which is the first one here, 10.3 microseconds, which is the second one here, and the third one is 10.8 microseconds. So these three different pulses are corresponding to three different paths that goes by ray number 1, 2, and 3. Alright, let's look at part 2 of question C. So at t equals to 0, a single pulse of light enters the optical fiber of length 1 kilometer, and this pulse lasts for 0.1 microsecond as well. So the questions want us to draw the pulses of light that leave the fiber. So by using the information from figure 9.3, so let's first put the marker of the position where the pulse is going to exit the fiber. So first, the pulse that follow the path of ray 1 is going to leave the fiber at 5.0 microseconds, and then the pulse that follows the path of ray 2 is going to leave the leave the fiber at 5.1 microsecond time, and the third pulse, which is the one that follows the path of ray number 3, is going to leave the fiber at 5.4 microsecond. Alright, so after we put the position marker of the pulse, because the width of the pulse is 0.1 microseconds, so we just get them connected. So this is the block for ray number 1, and then the block for array number 2 is here, which extended to 5.2, and then the block for array number 3 is going to extend itself to 5.5 microseconds because of the width of 0.1 microseconds. Yeah, so this is the signal that we get. And let's look at part number 3. Figure 9.4 shows that a pulse of light lasting 0.1 microsecond when it enters the 2 km optical fiber becomes 3 pulses lasting in total 0.9 microsecond when it leaves. In a telephone conversation, a series of pulses is sent along the optical fiber. It is important that no light from one pulse overlaps light from the next pulse. A second pulse of 0.1 microsecond must enter the fiber at least 0.9 microsecond after the first. And the question wants us to estimate the maximum number of pulses of light that can enter the 2 km optical fiber in 1 second. So this is actually kind of straightforward, because by looking at the diagram here, we know that a single pulse is actually extended into a block which consists of 3 different pulses with a width of 0.9 microseconds. So if you take this as a single unit of the information or a pulse, then what happens is that the maximum number of pulses that we can get in 1 second is simply given by 1 divided by 0.9 microseconds, and this will be equals to 1.1 times 10 to the power 6. So the maximum number of pulses that we can get for 1 second without the pulse being overlapping one another is about 1.1 million pulses. Then part 4. The question wants us to explain why this type of optical fiber is not used to transmit data at high rates over very long distances. So if we compare this diagram and the other diagram, so this diagram here is a signal that we get from the exit of a 2 km long fiber, and then this one here is the signal that we get from a 1 km long fiber. And one observation that we can see is that the separation of the first pulse to the end of the third pulse for the 1 km fiber is only 0.5 microseconds, and when it comes to 2 km it becomes 0.9 microseconds. So when the distance is long, what happens is that the separation between the first and the third pulse is going to become larger and larger. So if this number here become larger and larger, then what happens is that the number of pulses that we can send in 1 second is going to reduce. So there are two reasons. The maximum number of pulses is going to reduce by having a multi-mode fiber over a long distance, and then because of this, the rate of information transfer is also going to be limited. So the solution for this problem, although it's not not asked in the questions, we can actually tackle the problem by having a single mode fiber. And the reason for using a single mode fiber is that there will be a single pulse at the exit corresponding to a single pulse at the entrance.